kind of thought that meme was a little bit appropriate. Okay, so you may have seen this problem before. I think I've used it. Shout out to all my DOF boys that worked on this problem last night and gave me the trial run. So we've got two identical squares lying inside a unit square being 1 by 1. Find the width of these rectangles. Alrighty, so there's going to be a hint about to appear. If you don't want a hint for this problem, then pause now. And the hint that will help solve the problem, make it a little bit easier for you, is if you let that angle there equal theta. Okay, solution time. So if you were solving this problem without that hint, you would be starting with the x up in the top left corner being the width of the rectangle. With the unknown theta there, it makes it easier because we bring in a whole heap of trig. And often trig, the ratios, the identities, help us solve things quicker. So first up, we put on the diagram everything we know. Now, there are a bunch of similar triangles. It's easy to show that they're similar. If we consider the big triangle here, theta there, underneath that's 90 degrees. To the left of it's another angle, let it be alpha, for example. Along the straight line, we've got an alpha, we've got another 90 degrees, and we've got, therefore, that small angle down the bottom left must be theta, and it just follows around. They're all similar. And then x up in the top left corner, the width of the rectangle we're trying to find. We know that that's sine theta. The hypotenuse of that right angle triangle is 1, and the angle's down the bottom left, so therefore the opposite side must be the sine of theta. This one's x times the cosine of theta. The hypotenuse is x. With a tilted rectangle, it's identical, so the hypotenuse there is x. Similarly, down the other side, that helps us form two equations. The equations are in terms of x and theta. We need to get rid of theta out of these because we put the theta into the problem. But it turns out it's hard to eliminate theta from it because it's inside the trig parts. But you can eliminate x quite simply. Rearrange, make x a subject of the first one, make x a subject of the second. Similarly, for this step here, there was a common factor of x times 1 here and x times cosine theta in that term. So 1 plus cosine theta all times x, hence why there's that denominator. If you equate those two expressions, because they're both equal to x, cross multiply, and then use one trig identity, you end up getting an equation, a quadratic expression, 2 sine squared equals sine. Now, this has two solutions to it. A common mistake that's made by students is to cancel a sine on both sides. Technically, sine theta can equal 0. It can also equal a half. So if you solve that quadratic properly, notice first of all that sine theta can equal 0. For this particular question it can't though, because that would mean sine theta must equal half. Now at this stage, think about what you're trying to solve for. You want the width of the rectangle, you don't want the angle. So it's unnecessary to inverse sine this and find theta when we're going to just be taking the sine of it again to put it back in the x and taking the cosine. So if we've got the sine of theta, we leave it as a half. We need to find the cosine of theta. This is a common theme that you've been seeing in some of the videos. You make a triangle. Adjacent side must be root 3 if the hypotenuse is 2 and the opposite's 1. Therefore, cosine theta is root 3 over 2. Sine theta is a half. Cosine theta is root 3 over 2. Put those into either of the x expressions, whichever you fancy, and then you should end up getting 0.2679, or 2 minus root 3 if you rationalize the top and the bottom. Rationalize the denominator and write it as a nice surd. Alrighty. Extension questions, can you solve that using a conservation of areas approach without trigonometry? So you might use other geometry but not trig. And that's the starting diagram for it. It's a similar diagram except A's and B's in there as opposed to thetas.